Thank you for being here. I'll talk a little bit about the sensors in Android Wear. But first of all, if you look in the market for the last couple of years, 2 or 3 years, you'll notice that there's proliferation of sensing devices, starting with Nike Fuelbands. A lot of these are sort of on your wrist, sensing your movements. And then over time, when it's become crowded, people come up with more creative sensing devices. There's one on top, they said sensing on your ankle is better for biking applications. There's some on your pocket and some on your back for your posture. The one on the top right corner is actually more creative. It says, sense better is on your ear, so it's designed something put on your ear that can sense your movement. So all these trying to monitor your movement, sense sort of fitness application, track either step counter or some more advanced in posture or fitness, like a repetition count. But if you strip them away, look inside, really there are just one or more of these combination of sensors. There are really 3 types of sensors you can use. One is accelerometer, gyroscope, and magnetometer. The reason is because we haven't discovered a new physics phenomena that allows us to measure movement in a different way. So really all of them are using is just these 3 sensors. Some are just using one, like the pedometer, probably just use accelerometer. So what happens over time is these sensors got commoditized. They even sense put all of them in a single chip. Very cheap, you can buy them. So it really enabled a lot of these sensing devices. So now if you have a sensing application, you may be tempted to develop one of those sensors and do a Kickstarter campaign and everything. But here I'm arguing that you shouldn't do that at all. If you look at the smartwatch coming on the scene, and this is all the Android Wear watches coming out. The top 3 watches are already in the market. There's 3 more coming by the end of the year, and a lot more coming next year. All of them has these sensors built in already. Actually, all 6 of them has both accelerometer, gyroscope, and magnetometer. Some older watches, like Samsung produced these Tizen watches. Sony has a bunch of watch. Qualcomm has a watch. All of them have sensors. The only sort of exception I know sort of doesn't have all the sensors is Pebble. Pebble only has an accelerometer and magnetometer. But everything else, as far as I know, they have all those motion sensors. The reason they built this all in, number one is because it's really cheap. Number 2 is just because, like Johnny Ive said, watches is something really personal. It's on your wrist all the time. All of a sudden enable a new different class of application that was not possible with your mobile phone. So if you're looking into new opportunities these watch creates, motion sensing is really a good category thing to look into because it wasn't possible to do. Now it's on your wrist. These manufacturers see this as an opportunity. They build it in. So we may as well just utilize it. You may still argue that you want to build your own sensor because you want to strap it to your leg or somewhere else. We're going to run a Kickstarter campaign tomorrow. Oh, actually, let's start it. So first of all, the reason why all of these really sensors built in is sometimes manufacturers even take granted for it. This is a spec sheet for Motorola 360. If you look at their spec sheet, they said they have sensors, they have pedometer, they have optical heart rate monitor, but they don't even mention motion sensor at all nowadays because it's assumed it's a given. So you look into the product, it's in there already. They just don't even bother to advertise it. So this is the part I'm talking about, our Kickstarter campaign tomorrow. It's our novel band solution for a smartwatch. So if you want to strap it to your wrist, strap to your leg, anywhere, you can invest in our Kickstarter campaign. We spend a lot of money on it. It's ready built, already on Target shelf. If you support us in the next 24 hours, we even throw in industrial strength band solution that if you want to strap it to a rocket, you can do it. So I want to talk about not only hardware is there already, the sensing is also easier on the smartwatch. The reason is as follows. If you like a watch, you look at the sensor, they all have a reference frame. So the landscape direction is X, and the portrait direction is Y, and common for the phone is Z. So if you were to sense with the phone, it's a lot harder. My company, we actually started a couple of years ago thinking about tracking fitness with mobile phone, and which encountered a lot of problem. Number one, we don't know where the user putting the phone. It could be in their pocket, and once they're in pocket, we don't know which orientation it is. It could be facing down, sideways, upside down. We could ask them to put in their hands, and the same orientation problem. You don't know which side is facing, so you have a lot of things you have to consider. But nowadays with watch, it's really simple. You know axis is going away from the arm. It's fixed. It's the same X, Y, Z coordinate. But because the watch is on your wrist, you know how the watch is oriented. So if you, for example, detect that the X-axis is pointing up, you know their arm's up. You don't have to worry about the orientation stuff anymore. So there's a little complication if you want somebody wear their watch on their right hand. The only thing it does is flip the X sign. So you know the minus X goes up, maybe its arm's up. You still have to consider that. So there's two possibilities to consider, but it's a lot easier to consider mobile phone. Just you can't tell user to hold it in particular way or put it in particular location. So I want to give you a little example of what you can build. These are our own mobile apps. We're a startup company. We specialize in understanding these motion sensors on smartwatches and turn them into motion sensing apps. So I thought give you a little bit of sense of what you can build. This is a fitness app we built, and there's a fitness coach on your mobile phone, tells you to do different exercises. We come up with a different exercise for you to do. It depends on your fitness level. And the critical thing is that smartwatch. While you're doing exercise, you use your smartwatch, follow along, and we basically take the mundane task of tracking your fitness, the number of repetitions out of the equation. So we track your repetition, we tell you how many calories you have spent, and then you have a nice log, then you have to write anything down, and you can focus on the form. This app is called Vimo Fit, is in the Android store already. And this is another app we built. This is a little different. It's a very high precision sort of app. So if you're a golfer, you really wanted to know how well your golf games been going, how you improve the swing. So in the past, people buy these golf analyzer products. It's about $150. And if you strip away that box, essentially it's just 3 sensors that we've seen in the smartwatch. Again, physics, we haven't have the new laws yet. So it's all sensing by the same principle. Now you have a smartwatch. We can you basically wear your smartwatch on your wrist and do a golf swing, and we can tell you your angle, whether you're hitting the right way or you swing the right path, and tell you how to correct that. So hopefully I convinced you that hardware's there already, software is easy to do, and maybe you have some inspiration from these how to develop some other motion-based application, maybe turn your wrist to turn on the light, turn the other way to turn off the light. I wanted to spend the rest of the talk sort of give you a little sense of the different sensors available on the smartwatch, their strength and weakness, so that when you start to program these, you know how to best utilize them. I'll start with accelerometer. It basically tells you the acceleration in X, Y, and Z. And the good thing about this sensor is because of gravity, there is always acceleration on this particular sensor. And from that, you can tell the orientation of this device. So if I'm raising my hands up, I see acceleration going to the minus X axis. You get the, you got a positive rating on it. But you know it's raising the arm up or down because of gravity. And because there's you can have user acceleration on top of it, not necessarily acceleration. You have to do a little bit of work to filter out whether it's gravity or something other acceleration user inserted on it. But it's really easy to do. Basically, if you just go for a primitive form, you can do a high-pass filter or low-pass filter, really get out of the transient component. Because you think about having these phones, you're not going to accelerate it infinitely. It's really transient. You shake it, and it will have to come back, because this is not rocket longitudinal as a field. So you know the static component, that's sort of roughly your gravity. The problem with the accelerometer is really only measuring your acceleration. And if you have an application you want to measure displacement, like distance, how far I moved left or how far I moved to the right, it's really hard to do with accelerometer. The reason is because if you go back to physics, from acceleration, you can go determine the distance, like d in the equation. It's a 2-order of integral. So every time you do integral, there's constant factors comes in. First of all, you don't know the constant. Second of all, is when you do 2 integrals, it's a function of t squared. So as time goes on, even you have a little mistake in your acceleration measurement, it's just going to go exponentially big, so that it's really hard to measure the distance. And there are other ways around it, so just wanted to be aware the limitation of accelerometer. The other thing, key sensor is a gyroscope. If you think about, so first of all, gyroscope tells you the rotation around different axes. It tells you rotation speed. That's the basic measurement they tell. So if you rotate this phone, rotates this way, you see a rotation speed around the z-axis. And from speed, you can do an integral, 1-level integral to determine the angle, how far you have turned the phone. And this sensor is really good. It has very fast response, very accurate. It tells you the speed very accurately. And because you just do 1-level integral, you can determine the angle you're turning very, very accurate. Compared to measuring distance, this is night and day. If you just want to measure angle, use the gyroscope. It's so much easy. So if you think about, sorry, someone cut off over there. If you're thinking about what the accelerometer gives you a sense of your orientation up and down. Right? If you know the watch is pointing down or pointing up. Because gyroscope tells you rotation, now you can have a sense of your orientation laterally. You know which direction you're pointing to. So at least you know you're rotating on the lateral plane. So you not only know the rotation around the vertical plane, now you know the rotation around the lateral plane. The problem with gyroscope is that, number one, there's no orientation reference, meaning that you only know it rotated some way, but you don't know where it started. So I don't know I'm facing north, now I'm turning. So you can only measure the delta with it. The other problem with the gyroscope is because it's measuring rotation speed, you'll notice there's a drift if you're just measuring the angles, because you do an integral of that, and once you do 1-level integral, there's a time constant in that angle calculation. So if you make a minor mistake or there's a sensor noise on the speed measurement, then you'll see a constant shift in the angle gradually over time. It's not that big a deal. If, like in the golf app, we don't even need to worry about it, because you swing like in 1 second or 2 seconds, the drift is very small. But if you are thinking about some other longer time frame applications, then you have to take into consideration the drift in the sensor. This is the third fundamental sensor, magnetometer, basically measure where the north is. It gives you a fixed frame of reference. You really know where the north is, right? Especially if you have GPS, you can pinpoint exactly where the north is. It differs a little bit, depends on which part of Earth you are on. So from that perspective, it gives you the same functionality as the gyroscope. It tells you sort of your orientation laterally. Okay? Remember the accelerometer tells you orientation vertically, and now this is another sensor that tells you the orientation laterally. So from that perspective, it's a little bit duplicate in terms of functionality. Like this, I have this cheap Samsung phone. It basically just had accelerometer and magnetometer. They didn't bother to build in the gyroscope, that they don't need a precision kind of sensing application. But on these watches, they all have all of that. So the good thing about two things do the same job is you can use them to cross-check each other, things that we call sensor fusion. Use one sensor to improve another one. The problem with the magnetometer is it's just pretty noisy. You have a compass app on your phone. You can put it on the desk. You don't move it, and you can see the needle shifts back and forth because it's trying to hunt to where the north is. So it has 1 or 2 degrees noise that keep on moving. And it's a little bit slower compared to gyroscope. It doesn't latch into things really quickly. So I'm talking about Android Wear watches. It's essentially running a custom version of Android. So the sensor interface is the same as Android sensor interface. I want to talk to you a little bit about the nice thing about Android, which is they provide a bunch of called derived software sensor. They basically fuse together different sensor together, give you sort of a software sensor, tells you a little bit more information. So if you look at the Android spec, it will tell you it exposes the accelerometer. At the same time, they will expose a gravity sensor and another thing they call linear acceleration sensor. This is what we talked about before, because the sensor actually senses both the gravity component and the user shake component. But now the Android framework helps you a little bit by separating them out. They do it a little bit nicer way. It's not like I said, just put the low pass and high pass filters, because that introduces a little bit delay. With what they're doing, sometimes they use the gyroscope to help you to compensate what the orientation is. So they compute this gravity change much faster, much more accurately. So if you want to do and use gravity, you can use a built-in sensor. Example is when we have the fitness app show you, sometimes we track, for example, the exercise is a jumping jack. Your arm going up and down, and that's an application where we use a gravity sensor to sense it. We don't want you to shake and be able to register a jumping jack. So by using orientation sensor, you know the arm's coming up and coming down. It's a lot more reliable sensing than just using accelerometer alone. Another sensor they call is rotation vector. This is really giving you an orientation, the sense of orientation, where the device is, orientation-wise in the space. And this is a little bit sort of math intensive. It basically either gives you a rotation matrix or something called quaternion. That's the middle top thing that they give you. They give you a sort of matrix. What this matrix tells you is, if you look at any points on this your smartphone has its own reference coordinate system where X is going this way, Y is going up. And then there's also the world coordinate where north is Y and pointing up is Z. The other direction, east is X. So this rotation matrix basically tells you if you have a point on this watch and you apply this matrix transformation, it tells you exactly how it lands in the world's space. So this is the most powerful way expressing the orientation change. So anything you want to know what happened to your watch, and orientation-wise, you can essentially apply a matrix transformation to understand how it lands in the world coordinate system. And there's two ways to get the rotation matrix. One is they have a sensor called rotation vector sensor. You can just hook into that yourself. Or you can hook into the gravity sensor along with a magnetometer sensor. And using two sensor output, they have a helper function give you the rotation matrix out of it. Another thing they give is called orientation sensor. Again, this is a derived sensor. It tells you three parameters called the pitch, yaw, and roll. The way to understand this terminology is it came from aviation. If you imagine your phone is an airplane and it's flying forward and long lengthwise, pitch is really telling you, are you going up or going down, your airplane? And roll is telling you, are you rolling left and right? Right? Imagine an airplane, roll left and right, you have to turn. And then yaw is basically direction. Yeah, you're going north or south. So if you think of this as an airplane, it's much easier to understand this terminology. The problem with this sensor is this is a problematic notation of orientation. If your airplane is going up, it's not clear when you do turning, is it roll or a pitch or yaw. It become ill-defined in that area. But if your application is sort of like airplane flying application where you never go up, this is a lot easier to understand than the matrix transformation. So you may be able to just leverage this to solve your problem. I mentioned key thing you do on these sensing is you wanted to understand the limitation of these sensors and be able to combine them together to give you the necessary output I only have one slide to talk about this. This is sensor fusion, basically people talk about. Taking two sensor outputs and massage them so that you can get a better sensing. And this is an example of sensing the magnetometer and using the gyroscope and magnetometer together. So the magnetometer, you can see that the raw input is very noisy, but the gyroscope has this drift problem I talked about. So if you see the graph on the right, you see the gravity, the gyroscope actually drift over time. But by combining the two sensors together, in the algorithm side, you can take advantage of both sensors. You can get a fast response from gyroscope, then at the same time eliminate the drift by using magnetometer to compensate for it. That's it. My name is Juan. We have a company called Vimo Labs. We're focused on these wearable mobile applications. If you have any question about how to program these sensors, feel free to ping me. Thank you. Yeah.
So you've got the sensor, you've got a certain, you know what the orientation is from the wrist.
Yeah.
But there's 6 degrees of freedom in the wrists
Yeah.
that you're not able to account for from that orientation.
Good question.
Which is the absolutely crucial part of the golf swing. So I was wondering, in terms of providing feedback to the user out there.
Good question. So this is the other aspect I did not stress. You understand your application. You have to take into account the things you can leverage from an application. A golf swing, you're supposed to hit it straight. Your arm has to be straight. If you're angled this way, you're wrong to begin with anyway. So we'll report things wrong. But if you're a reasonable golfer, you know from day one your arm needs to be straight. So we're taking advantage of that fact. We compensate a little bit, but if you're doing this, your way will be off.
But your arm can still be straight. You can have your wrists cocked like this.
Yeah, then we know you're turned.
So you're going to,
You turn. Look at the arm. If you're doing this, your arm's turned. You can sense that minor difference.
okay.
Yeah. Thank you.